Statistical interaction describes a relationship between two variables that is dependent upon or moderated by a third variable.
For instance, do you prefer ketchup or soy sauce? Obviously, your answer depends on what food you're eating. If you're eating sushi, you probably prefer soy sauce. And if you're having a burger and fries, you're probably going to want ketchup.
In this case, the third variable is referred to as the moderating variable, or simply the moderator. The effect of a moderating variable is often characterized statistically as an interaction, that is, a third variable that affects the direction and/or strength of the relation between your explanatory or x variable and your response or y variable. What if the population we're studying has different subgroups? Could it be that, like the soy sauce ketchup example, different subgroups could have a moderating effect on our association of interest?
To explore this idea, we're going to use a hypothetical study and some made-up data. In our imaginary study, we're looking at two diets and their effects on weight loss. Diet A is a low-carbohydrate plan. Diet B is a low-fat plan. Our hypothetical study also recorded data on which exercise program participants chose, cardiovascular exercise or weight training.
Our variables of interest are diet and weight loss. We've added this third variable, exercise plan, to help us understand moderation or statistical interaction. So what's the association between diet plan A and B, our explanatory variable, and weight loss, our quantitative response variable? This table shows our hypothetical data showing diet, weight loss, and exercise plan. Since we have a categorical explanatory variable, diet plan A or B, and a quantitative response variable, that is, weight loss, we will of course need to use analysis of variance to evaluate the association. As you can see, we're testing the association between diet A and B and weight loss. There are 40 observations in the data set. The f-value is 12 and is associated with a significant p-value, that is, a p-value less than 0.05. While this tells us there's a significant association between diet type and weight loss, to understand that association, we need to look at the output generated by the mean statement. Here we see that the average 1-month weight loss for diet A is about 14.7 pounds, and that the average 1-month weight loss for diet B is about 9.3 pounds. So, in conjunction with a significant p-value, we can say that diet plan A is associated with significantly greater weight loss than diet plan B. Here we show the finding graphically as a bar chart with diet, the explanatory variable, on the x-axis, and the mean weight loss, our response variable, on the y-axis. But what about our third variable, exercise program? Would we get the same results in terms of the association between diet and weight loss for those participants using cardio and those participants using weight training? In statistics, moderation occurs when the relationship between two variables depends on a third variable. In this case, the third variable is referred to as the moderating variable, or simply the moderator. The effect of the moderating variable is often characterized statistically as an interaction, that is, a third variable that affects the direction and/or strength of the relation between your explanatory and response variable. So, does type of exercise program affect the direction or strength of the relationship between diet and weight loss? The standard way of asking this question in the context of analysis of variance is to move to the use of a two-way or two-factor analysis of variance rather than the one-way or one-factor ANOVA that we've been using. Instead, we're going to take a less standard approach that can be consistently used across each of the inferential tools, that is, ANOVA, chi-square, and Pearson correlation. In each of these contexts, we're actually going to be asking the question, is our explanatory variable associated with our response variable for each population subgroup or each level of our third variable? That is, are diet type and weight loss associated for those doing the cardio exercise program, and are diet and weight loss associated for those using the weight training program. To accomplish this, we're going to run two separate ANOVAs, one for each level of the third variable, that is, for each exercise program. The ANOVA table examining the relationship between diet and weight loss for those in the cardio exercise group shows a large F value and a significant associated p-value. When examining the means table, we see that for those involved in the cardio exercise program, Diet A is associated with greater weight loss, 20.5 pounds on average, than Diet B, which is 7.1 pounds on average.
The association between diet and weight loss for those involved in the weight training exercise program is also significant. It has a large F value. However, the means show that the association is in the opposite direction. For those involved in weight training, Diet B is associated with greater weight loss, 11.5 pounds, compared to Diet A, only 8.8 pounds.
Here, these results are shown graphically. As you can see, the relationship between diet and weight loss depends on which exercise program is being used. When using cardio, Diet A is significantly better for weight loss than Diet B. When using weights, Diet B is significantly better for weight loss than Diet A. Thus, we can say there's a significant statistical interaction between the variables diet and weight loss, and the type of exercise, our third variable, moderates the association between diet and weight loss.
Suppose that we did not evaluate exercise as a possible moderator and instead focused only on the association between diet and weight loss for the entire population. Based on this graph, obviously, we would have incorrectly concluded that Diet A is better than Diet B. As we now know, that is only true if we're looking at the cardio group.
Now, let's evaluate third variables as potential moderators in the context of chi-squared tests of independence. For this, we're going to return to our original SAS program using the NESARC data and asking the question, is smoking associated with nicotine dependence? As we can see from the large chi-square value and significant p-value, smoking quantity and nicotine dependence are significantly associated. In examining the column percents here of each smoking group with nicotine dependence, we see generally higher rates of nicotine dependence among groups that smoke more. So among non-daily smokers, only 25% are nicotine dependent. Among those smoking 1 to 5 cigarettes per day, indicated by a code of 3, nearly 50% meet criteria for nicotine dependence. Those numbers increase with higher levels of smoking. This gives us the graphic representation of this positive linear relationship. As smoking quantity increases, so does the proportion of individuals with nicotine dependence. This finding is accurate with regard to the larger population of young adult smokers. But might a third variable moderate the relationship between smoking quantity and nicotine? Put another way, might there be a statistical interaction between a third variable and smoking behavior in predicting our response variable, nicotine dependence? We're going to evaluate major depressive disorder as the third variable. Our question will be, does major depression affect either the strength or the direction of the relationship between smoking and nicotine dependence? Put another way, might a third variable moderate the relationship between smoking and nicotine dependence? Is smoking related to nicotine dependence for each level of this third variable? That is, for those with major depression and for those without major depression. You can see the crosstabs or cross-tabulation table looking at usual quantity by tobacco dependence in the past 12 months. First, for major depression equal to 0, which is those without major depression, the chi-square value is large and the p-value is quite small. In addition, the column percents reveal what seems to be a positive linear relationship, with percentages of nicotine dependence increasing between lower levels of smoking and higher levels of smoking. So we can say that this is a statistically significant relationship for those without major depression. For those with major depression, we find a large chi-square value and small p-value, which is statistically significant. These column percents also reveal what seems to be a positive linear relationship with percentages of nicotine dependence increasing between lower levels of smoking and higher levels of smoking. Using a line graph to examine the rates of nicotine dependence by different levels of smoking, it seems that both the direction and size of the relationship is similar between smoking and nicotine dependence for those with major depression and for those without, although those with major depression show higher rates of nicotine dependence at every level of smoking quantity. In this case, we would say a diagnosis of major depression does not moderate the relationship between smoking and nicotine dependence. For both young adult smokers with major depression and those without, higher levels of smoking behavior is associated with higher rates of nicotine dependence. So now, let's test for moderation within the context of our final inferential test, the correlation coefficient. You might remember this scatter plot and correlation based on the Gapminder data between rate of urban dwellers in each country and the internet use rate. We found that this was a significant association with a correlation of 0.61. But might this correlation between urban rate and internet use rate differ based on countries with different income levels?
To explore this question, we've created a third variable called income group, which is categorical.
When we examine the correlation coefficients between urban rate and internet use rate for each of the income groups, we find the following. For the low income group, the correlation between urban rate and internet use rate is 0.11, and the p-value is not significant. For the moderate income countries, the association between internet use rate and urban rate is 0.329, with a significant p-value at 0.0014. And finally, among high-income countries, the correlation coefficient is 0.089, again with a large p-value, suggesting that the association between urban rate and internet use rate is not significant for high-income countries. When we map these findings onto the associated scatter plots for each income group, we're able to better visualize the significant and non-significant relationships. Estimating a line of best fit within each scatter plot shows the positive association between urban rate and internet use rate among the moderate income countries, and almost no relationship between those two variables in both the low income and high income countries. Asking questions about statistical interactions can be an interesting way to explore your data and your associations of interest. This is not difficult to do using the skills you've acquired thus far. There are more advanced topics that we can cover here, such as multivariate techniques, that can be very powerful. But even without these techniques, we can still use bivariate inferential tools of ANOVA, chi-square, and correlation to describe our sample, make inferences about the larger population, and really begin to understand what relationships these associations hold under what conditions or at what levels of our third variable. Now that we've found associations, can we assume that association implies causation? We'll answer that question soon.